afternoon, everyone. Welcome to the seminar. And it's my great pleasure to introduce our guest today, Professor Santosh Devasia. Professor Santosh Devasia is a full professor at the University of Washington. He obtained his bachelor's degree from IIT in 1988 and master's and PhD degree from UC Santa Barbara. He spent a few years in University of Utah, before he moved to the University of Washington. And he has been having a fantastic career path, and he's a role model for me personally. So some of his papers are continuously being highly cited in the area of info control, and he has been a number of important roles in the faculty members in the division of mechanical dynamic systems and control division in ASME. So he has a long list of resumes. So right now he is the director of the Boeing Advanced Research Center, BARC, at the University of Washington, and he has served as the associate dean for the School of Engineering at UW. And he is the general chair of the 2020 American Control Conference, a fellow of ASME, and it's my great pleasure to introduce his talk today, Synchronized Networks Using Delayed Self-Reinforcement. Let's welcome the speaker.
Thanks, the department and the center to invite me here, so it's a pleasure to come visit. It's always good to see new schools and see how things are going on. So I never had a chance to visit Connecticut. It was wonderful. And the weather is, cold but sunny, which is nice in Seattle. Seattle's rainy, right? So, I'll start with a brief intro to the University of Washington and BARC, and then we'll go through the research topics. So, obviously, we're on the other side of the United States, pretty much on the other end. And so the question I always get is, how much does it rain in Seattle, right? So it's famous for its rain. So in Seattle, we get about 37.1 inches of precipitation. This is an average, from Wikipedia. Okay, so how about sunny Texas? Dallas gets about 37.5. Okay, you wouldn't think that, right? Florida gets more than that, actually. And New York City, which is close by here, is about 49 inches of precipitation, right? So it's not much in Seattle, except the difference is that in Seattle it rains pretty much, once in a while, every year long, right? So it's like evenly distributed. Maybe most other places maybe it comes once in a while and then you're done with it, right? So that's the difference, right? So, okay. But of course, the rain makes Seattle wonderful. So Mount Rainier is spectacular. The view that I showed in the very beginning was a view of Mount Rainier from the campus. It's really beautiful. The cherry trees are wonderful. They come in March, and it's a really special time in the campus. And of course, the campus in overall place. If you look at the typical weather, the U.S. weather, right? So rain in Seattle implies that, Seattle is right here. That means the jet stream is going up, so it brings rain to Seattle, goes up, and then comes down again, lifts back again. So it keeps the frigid air up in Canada, right? That means good weather in the Midwest and the East. Now, if it's not raining in Seattle, like, last week when I was just coming back, it was really sunny. That means the jet stream has pushed upwards a little bit. And that's really bad because then it comes down and the Midwest and East gets really bad weather. So when it rains in Seattle, it's good for you guys. All right. So University of Washington at a glance. Okay, so this is the central part of the campus. And so you can see the cherry trees in bloom, and this is from one of the expositions they had long time ago. The big fountain in the center of the campus. Founded in 1861, so in pretty old school on the western coast. It's considered number one in federal funds for public universities for a very long time. They have an incredible medical school. Ranked number 11 by the old U.S. News and World Rankings. And it's got about 45,000 students, in the campus, on the main campus. Roughly about 7,500 bachelors per year. So, the College of Engineering, we are about maybe 269 faculty members recently. And we are very proud of the fact that we have about 24% women in the College of Engineering. Okay? We put a lot of effort into that. It's comparatively a smaller graduating class. We only have about 1,000 students graduating every year from the campus, partially because it's constrained, space constrained. We can't take more people. Research funding is about $53 million a year. 15% of that comes from industry, from the local industry. So it's a big component of industry inside. And the other cool thing about our college is that the UW is considered now the most innovative public university I think in the world, if I remember right. We have about 85 companies that got started up. So we also have an innovation approaches here. And they help you to start companies. That's one of the things that's come up. And what's also cool is that faculty in the College of Engineering is about 10% of the campus, but we are about 50% of the IP in the new companies that start. But the rest half is the medical school. So, other than the rain, what else is Washington famous for? So if you look at it, Boeing started out so it's a well-known company that people know about. Microsoft is a Seattle company, right? Starbucks, which is cool. Most people have heard about Starbucks around. Wherever I go, then Washington apples are pretty good. UPS is a very old Seattle company. Costco. Manufacturing is hot. Although there's a lot of high-tech companies, manufacturing is also very big because aerospace, Boeing is there, and Packard, which is the biggest trucking company, is Seattle-based in North America. And of course, Amazon is a big gorilla now. They're buying all the big buildings in downtown Seattle. Okay, and the new thing that's coming up is the space industry. There's a budding space industry that's coming up from Blue Origin because of the University of Washington. So overall, what is interesting is we have a very good industry which is very close in a sense because pretty similar to here. You have this big companies which are very close to campus. So we had a college-level strategic plan a few years ago, and we just talked about, what should we do, right? I mean, this comes up every time you have a new dean, you have this process going on, right? So I'm sure most of you are familiar with it. And one of the things we thought is we can strengthen our industry partnerships. So a typical model is in industry give you money, maybe after 6 months or a year, you report back, right? And of course, what they're most interested in students, and sometimes IP. So this is a traditional model, and then what we were thinking about is trying to do co-location because we're this close. The question is, can we bring these two more closer to each other? And it's perhaps similar to the UTC model. I was learning about your UTC models recently, but I haven't gotten the full picture yet. But it's something similar to that. Yeah. And so the first major co-location at UW is this Boeing Advanced Research Center. We'll talk about it briefly. And then these are the other things. We do have some collaborations with most of these companies, but those are the things we're trying to build towards. So in the mechanical engineering department, so Boeing, this BARC Center is housed in the mechanical engineering department. It got initiated. As you can see, these things are difficult things to do in general. There's IP issues, there's space, there's new things that are really difficult. So leadership is really helpful to have the right, help push us into some places. It helped to launch a BARC lab, and then we are working with Packard to create a Packard-type center in there. And industry capstones, which you have a lot, I heard. That's also very helpful, very good for the students, right? So briefly, the Boeing Advanced, it started in 2014, fall, so it's been 5 years roughly. It's got a co-location space in campus. The main areas are basically big data and machine learning approaches, robotics and ergonomics and safety. So when you're doing some machining operations, there's lots of ergonomics issues, so you can do some robotics for that, and then composites. And the fun thing for students is that you actually have real mechanics coming in to do testing and stuff. That makes it really exciting for them. And from the university's point of view, it's important for education. So it goes bachelor's level students, master's level students, and PhD students, right? And students learn by doing, and they're probably the most highly motivated students to work in these applied areas. I mean, I've teaching capstone designs all through my life, right? So once in every alternate year I teach that. But I've never seen students that excited about a project, I must say. Okay? So it's definitely a very high impact collaborative research that you can do. Okay? And it's really a source for problems with strong potential impact. Okay? So it's rich problems inside if you look at it. Now, how to work together, this is a work in progress. Okay? So, there are lots of challenges. You have to learn how to work together with the industry partner in that setting. So one is IP, who owns the IP, how does the industry acquire it? Second is research needs. Industry needs are fast. They want maybe next year, 2 years down the road. The rest of them is, that's a little bit different ballpark. And then versus deep dives that we would like to do, right? We see rich problems. I'm going to work for it a few more years, but time to move on, right? So those are some of the challenges. And then funding cycles. Some simple things like their contract starts from January and ends in December, right? And our students start from fall and then they go to summer. So if the contract comes in January, you may not want to have students around for that matter. So these are some of the nuances that you have. And I thought I'll at least mention some of the fixes that we have. Not perfect, but some of the things you can do is, for example, IP, we have prepackaged IP. So they pay upfront a fee, like 5%, 10%, depending on the company. And we give the IP back to the companies. And conceptually, we actually tend to make more money that way than we do with the other methods. Research needs, so we have this deeper set of problems. We usually leverage either federal funds or state funds to do those things. We also have a mix of students on each project. So the PhD student is almost like a TA kind of thing, and then we have masters and undergraduate students who help out with the day-to-day kind of things. The funding cycle thing was a challenge. So we do some return overhead back to the lab, so we can manage the students across years. And also we have some professional master's programs. Okay. That helps bring that. Okay. So that was my brief intro to the campus. So you have some feel for the things I do from an administrative point of view, and also some research. So I worked a lot on atomic force microscopes and so on, but right now I have two major interests. Okay. One is on human-robot collaboration. This is somewhat inspired by the BARC projects, and I'll talk about briefly, and then I'll go to today's topic, which is on propagation of distributed systems. So the first area I'll illustrate by three applications. Okay, this is human-robot collaboration. So this first project, so you have a robotic system that's probably drilling a hole. Now we're talking about confined spaces like the wing. So it's not so lighted as this. This is because you can see what's going on. So lighting conditions are bad. You cannot put external sensors around because putting a sensor itself takes a lot of effort. Okay? So under those low sensing environment, how do you localize the systems becomes difficult. Often people are crawling into these spaces. The spaces are about this high. Okay, and they're doing sealant operations and things like that. So if you like to make a robotic system inside that, especially you have to put lightweight robots inside, it becomes really challenging because they're flexible, they don't do as good as the big, enormous robots that they usually use. Okay. And so that was a question we were trying to do. And so some of the research challenges are, you have conflict between a human and machine. If they're both operating at the same time, who should have authority, right? You can always give the authority to a human. That means the human is always doing things, and humans are slow to the operators. And also the second question we're trying to figure out is, can the machine learn from the human demonstrations? So as a human is showing things, can you localize, for example, if you know where you are, and then maybe you can do things faster. Okay. So the key ideas that the students were using is to try to use the human forces, the forces that the robot is feeling, and using that as a measure to quantify off-normal events. The second topic is Jonathan. He built up, robotic prosthesis. This is prosthesis. We are working with VA Hospital on trying to put a prosthesis on lower limb amputees. Now, active prosthesis is around for a long time. So when you talk to the prosthesis people, what they'll tell you is that most of these active prostheses, which are like 75K each, they are set up just at the factory setting. It's not tuned at all. Why? Because when you get paid money for the prosthesis, but not time for the prosthesis to tune those things, right? So that's where the funding comes from. But anyway, it's difficult to tune. It takes a lot of time and effort. It's not easy. So what happens if the prosthesis is trying to figure out how to tune itself while you're also learning how to tune itself? As with any coupled system, there's a problem when you couple these things, right? And so when both of these things are learning with each other, how do you at least manage to make sure it doesn't blow up is the first question to ask. Okay, so that motivated me to do a couple of different projects. One of them was trying to think about if it's not humans, but let's say two machines or multiple machines, if they're learning together, can you come up with some convergence criteria? So the main result in that was, there was a way to partition the control authority among all the different agents, such that if the original agents were converging, the network also converges. Okay, so that's a nice result in Automatica. But then Jonathan took part of that because a human is also learning. Humans are difficult to model sometimes, so that's a little bit challenging. So his main work was trying to see, can you get, database methods for human models? I can use it to at least ensure you don't get divergence of these properties. Okay. The third project is by Rahul. So this one was because, in the factory, if you're doing teleoperation and things like that, it's usually people who are not very experts, in robotics operations. You can do teleoperation with the robotic surgery, and those are really good because it's a doctor, they've been trained, and you pay them a lot of money, right? But as a factory workers, they're not paid as much, they don't get as much training, and doing teleoperation is really hard. If you try to track something around 0.5 hertz, you start getting oscillations that makes your performance really bad. Okay, so because of the visual feedback coming to your brain. So the problem that we worked on was, okay, so if the robot knew what you wanted, like what you were trying to do, then the controls is not so difficult. Robot can build a controller that will track as speed you want. The challenge is that you're doing some actions as a human, right? And this is what you are trying to do. This intended goal in your head. So you're looking at the robot and saying, "I want to go to the left," and maybe you're doing an action with the Kinect system. But what your hand is doing is not what your brain wants the robot to do. There's a dynamics between your brain, your muscle, your hands, and all that stuff. And so what the human wants is not what the human acts on, right? So what we did is try to invert that model, model this system and invert it so that by looking at the human action, you can infer the human intent, and then the robot controls for that. And that was reasonably successful. We'll move on to today's topic. So this is on, so I got interested in information propagation in distributed systems. This was my last sabbatical last year, like Najat, I was traveling around. So I got a sabbatical, which is really good because it gives you some time to think. Usually you're so busy with things that you don't get time to think. And research on my own, which is always a pleasure to do. So UW owns a beautiful research center. It's in the islands, near the university. A little bit far from the university, it's in the islands. Of course, it's sunny even in winter, which for you probably is nothing, but for Seattle, because of the rain, you feel good to be there in the winter. The cabin rentals, you get beautiful cabins right by the sea, and the rental fees are very nominal. And anybody can apply, even you can apply if you want, right? If you want to go visit, it's an organization for any scholar, even artist from any field can apply. See, if you get time, you want to visit Pacific Northwest, it's spectacular. Okay. There's no TV, but really good internet. All right. Anyway, so I had some time and I was looking at swarms. And so the question is, why spend more time on swarms? The theory has been around for a long time, right? And definitely a lot of work on it. So I got motivated inside this because of, about the swarms, right? So it's flocking of birds, animals, insects, all kinds of things. And so the question is, how do they maintain this formation? Right? So this video is from a paper in Nature Physics in 2014. So this study, raised a lot of questions about existing models. Okay? So existing models are all diffusion based. So you look at we'll talk about it in detail later. But essentially looking at diffusion of the neighbors, and that information gets propagated. And what they found is that the speed of propagation is not the same. It's almost like a wave. So the models don't match what they're seeing, right? And so I got interested and said, "Oh, this sounds interesting. Why?" So I remember listening to somebody's talk, and they were talking about this. I thought, this sounds interesting. It took me a few years to get to that because you don't have time. Okay. All right. So that was my goal. I wanted to understand this problem. It sounded interesting. Clearly, there's interest because you like to know, how should I change this model so it can capture what you see in nature. That could be interesting just in that, for that. But certainly if you can do that, it may be good for engineered systems too. We got lots of swarms going on, UAVs, robots, drones of cars, and so on. So if you can bring that same ideas into engineering, it could be interesting too. Okay, so that was my motivation. So I'll clarify in the next few slides. The question I was looking at is, how fast can information propagate through a swarm? Can you increase that from what the current models are predicting? And then can we better match observations? So these were the things that interested me, and that's what I was working on the last year. Okay, so we'll go through a standard swarm model. So this is from 1992, something. It's an old model, and there's some previous papers before that too, but these are some classical papers that people refer to. So you have all these different agents. Each agent has an XY position and an orientation. Think of it as planar, because even flocks can be almost planar if you think of it. Okay? Typical swarms. You can also do 3D, but this is just a simplification, right? So you have X and Y, and you have orientation. And the speed is considered to be constant in these models. So they're going at constant speed, just orientations. Okay? So the update of the agents are simple equations, extremely simple. So the position at the next step is the previous position plus the velocity and the velocity in that direction. Okay? So you have the cosine or sine theta terms, and delta t is your sampling time. Okay? So what's amazing is that this extremely simple model captures this overall behavior really well. Okay? That's why it's very popular. And so essentially what you do is you change your orientation. That's what gives you maneuvers, turns, and so on. Okay? And often what happens, you'll see a leader making a change, and there's lots of research on how to choose a leader and all that stuff, but essentially somebody makes a change. And then the question is, how does that change propagate through the whole thing? Okay? All right. And it's really important that this information propagate rapidly, because otherwise it breaks apart. So here's a simulation of the same system. You can see something started moving, and it didn't propagate fast enough. I'll play it again one more time. So around here, these agents have decided to move, and that information is starting to propagate. You can see these are still going down. Okay, some of them have turned really little bit. Okay, and that's the crux of the problem. Now, how fast the information can propagate tells you how quickly you can maneuver all these other properties that you can get, right? Okay. So it's this lack of orientation, I call it synchronization, right? I mean, it's okay if all of them turn slowly. You don't care about it. Then it'll still maintain formation. But if they're turning at different rates, you're in trouble. So you want to tell them synchronize is the catch, okay? So typical consensus problems that people worry about, they worry about how do I get to the final state? But how you're going there is also really critical. And this research is about how to get there. You can get them all fast if you like, but getting there and how you get there is really critical. Okay? All right. So this is a toy problem the students are building in our labs. So, obviously platoons of cars, all these things have the same question. Now, if the speeds were synchronized, it was good, but the problem is they're not synchronized. If one of them stops and the other ones are not stopping at the same rate, that's when you get into troubles, right? So you can think about, you can get really high-speed motion if you want it, if were all moving at the same speed somehow. So again, synchronization is what I'm talking about, right? All right. Then you can get smaller spacing, higher speeds, and all the benefits you can think about. Okay, so now that I have sort of clarified this, a basic recapping a little bit, right? So you could do rapid maneuvers if you could to avoid predators and for better performance in engineered systems. But rapid maneuvers require synchronization of information. Okay? And for faster synchronization, you want this information to be transferred as fast as you can between the agents through the whole system. So in this picture, for example, if the agent is the leader is in the middle, then it has to get to all the other agents quickly.
Can I ask something?
Yes, Nathan, go ahead.
So now in this activity, we start with the presumption that the information is not local, but it is distributed. Is that right?
No, in this case, the leader is the one who is going to determine where the turn is going to happen.
So now
it's localized.
Decision is decentralized, and the communication and information is also decentralized.
Yeah, the communication is decentralized. The observations are decentralized. Control in that sense is decentralized. But the command is going to one person. Now, if you turn left loudly, maybe they could have all done.
Leader following type of...
There's a leader following kind of things, yeah.
But then you need some sort of a communication network, the topology, right?
Right. So the communication topology can also be added on top of this. But even without the communication issues, you still have problems, right?
Yeah.
So
the point that I was trying to clarify here is that when you say synchronization of the information, you really mean the members of the swarm are all informed about leaders' doings.
Yes.
Almost instantaneously.
Yes.
Okay.
If you can, hopefully, without a loudspeaker. Okay. Right.
Yeah. Most often, though, the neighboring agents are being followed by.
Yeah, this is what's going to happen here too. But that's the same paradigm here. So let's get to that. So very good. So let's formulate the problem mathematically so we're all talking about the same thing, right? So this is important. Okay, so we talked about each agent's position being updated based on its velocity. We assume all the agents have same velocities. You can make the problem more complicated, but this is the simplest level to come. And so the II, this one is the orientation in this picture, right? We call that as the information of each agent. Okay. So this is the more important step. So how does the orientation change? Okay. So the orientation changes. So this is ik plus 1 minus I. So this is how the angle has changed from one step to the other. That depends upon a few things. Okay. So this is a deviation of the agent. So the I is the current agent. Each agent looks at its neighbor. So its local information is looking around, finds the deviation between its angle and the neighbor's angle. And then does an averaging process. So how many of our neighbors you have, you average that. So it could be a chain, it could be any other 3D, it doesn't matter. So it's a localized, just as you would expect in the typical modes. Yeah. So you take that localized deviation and you add that as a correction term. So you're trying to go to the average, local average. Right? So that makes sense. And so this is time. That's just a time step for progression. This gamma is important. That's the alignment strength. How quickly are you going to try and arrange yourself to the neighbors? If you yank it up, you respond faster. Okay, you expect it. Matches what you're thinking, Najat, right? Okay, good. Okay. So this is the same equations from before, right? So the update of the information, or in this case angle, it depends on the local average of each agent. Now, if you massage this, take to the other side, divide by time, if you convert it, it's basically a diffusion equation. Okay? Just like heat transfer, the typical diffusion equation. So these are constants. Again, you have the alignment strength here back again. Okay, that tells you how quickly you're trying to arrange this. And the A squared term is the spacing between the agents. Okay, so this is a classical equation. People have studied that in many fields. And if you look at that equation, you can talk about how quickly does information propagate, perturbation propagate. Okay? And there'll be some coefficients that come about, but efficiently it's a square root of t phenomenon. Information will propagate as a square root of t, the distance it travels. Okay? So that's well studied, nothing new in here. Okay? So the other thing that happens in diffusion basically is that if you have some information here, it gets damped out as you go. So the first point might turn out hot, but as you go further out, it may not have as much. It's a damped phenomenon anyway. So these are the classical diffusion things. So if you take the classical models for swarming, this is what you should expect. Okay, so that's the state of that was the state of the art, right? So here's the that paper I was talking about in 2014. They took many swarms of birds, and they got data recordings of this, figured out how the birds are moving, their flights, velocities, figured out how information is spreading, empirical research, right? And they found that the data from the real frogs, and then they found that there's deviations from traditional models. And you can see it's almost flat. That's the other thing I wanted to show. Okay. And it deviates in 3 cents. Okay. The first one is that the turn information does not decay with distance. Okay. As opposed to diffusion models. The second one is that the information spreads proportional with time, not square root of t. So it's almost like a wave-like propagation. And the third is that the alignment, right, this information of how to rotate, travels much faster than neighbor rearrangements that you would expect. So it is not like huge neighbor rearrangements that's keeping the formation. It's actually this information of turns spreading through the system that's keeping the formation. Of course, you can do neighbor rearrangements too, but this is the key point. Okay? And so that's what I was interested in. So I was trying to see if I can do something with that, right? Okay. So now there are other current approaches that you can do to augment the system. So I'll cover a couple of them. Okay. So now on maintaining formations. So this is a more detailed model by Cousin in 2002, so about 10 years later from the original models, right? And it's very intuitive. Okay. So remember we talked about the update depending upon the neighbor rearrangements, right? neighbor, the difference between the neighbors. You're looking at that and averaging that. So in here, what you do is you make it a little bit more complex in the sense that if you're here, obviously you can't see everything, so you can put a cone of where you can see, where you cannot see. It also has this central cone where you're trying to do repulsion. If you're close, and you're trying to repel from those things, right? So you're not trying to align, you're trying to go perpendicular to that. Then if you're very far away, that means you lost your fog, you're trying to move towards it. So there's a zone of attraction, and this is where we're trying to align, orient yourself. So it's a more detailed model. And of course, how should you weight these things are interesting questions. Sometimes people just do it randomly. Which other neighbors can also be randomized. There's different aspects to this problem. And of course, it gives you a little bit better, fits to models. Nevertheless, as you saw in the 2014 paper says that this alignment information travels faster than all these rearrangements anyway. So the question is, if you can solve that, of course, the rearrangements can help you, but the alignment, the question is how quickly is the information? That's still the fundamental question. Okay? And so this space, distance-dependent rearrangements can help, but you still have to question about how quickly can you travel, send this information. Okay, the second approach is to tune up the alignment gain. And if you yank that up, it tends to respond faster. So you'll reach the final steady state faster. So of course that requires larger inputs. When you also have, it also tends to make the system more stiffer. When you have a stiffer system, it means your bandwidth has to be higher. Okay, so some standard problem that you run. Of course, the update rate tends to be limited by how quickly can you send something, how quickly can you communicate. So there's some limits to how much you can compress that. So in other words, the maximum update rate limits this alignment strength, and that in turn limits your information spread. So that's the step. Okay. So the proposed approach. All right. So back to the original equations. Okay. You take the average deviation from your neighbors, apply with an alignment strength the old equations. So the modification I have, okay, so remember this is the update, right? Update information. You take the previous update that you had, add a little bit of beta, this is a tuning parameter, and feed it back. So that's why I call it the delayed self-reinforcement. So it's not like extremely new data. You're not looking at for any other neighbors. You're looking at the same set of information you had. You're just using a previous update to strengthen itself. Okay. All right.
So this is kind of like the predictor-corrector time integration step.
Perhaps, but you're looking backwards in this case, right? And there's no new information. That's right. If you could correct yourself, that would be really nice, right? Yeah. If you can look forward, it would be really good. Okay. Yes. So we can't do that yet, but that'll be helpful. Yeah, but it's similar in concept. You're looking backwards and adding something. Mm-hmm. Okay. And so this beta is this update gain, and that's a tuning parameter you have. Okay. So it's reinforcing your old input. So you can rearrange it, bring the IK back to the side. This gives you the update log, right? Now, this kind of delayed reinforcement is referred to as the momentum term in gradient-based searches. In algorithms that do gradient-based searches, they add this term. 80s, from the 80s, right? I heard about that later on, but it was kind of interesting to know. But not used in network theory. Usual network graph theory, people don't usually use that. So, I want to talk in terms of implementation, right? So when you don't have the DSR, the delayed self-reinforcement, what each agent is doing is getting this average information from the neighbors, right? Updating its state, and then looping it around. Yes?
Now this beta and gamma are fixed for all the agents?
In this model, yes. Simple models, yeah. We could make it more complicated, but in this case, it's just fixed. So what I want to mention here is that it's not requiring any new information, right? It's only the old information that's being circulated again. So in terms of implementation, you haven't changed the amount of information you have. Okay? But it just uses a delayed version. So that's why I was reading up Nathan's papers, and no additional sensors, right? And the update rate is going to be kept the same. You're not even changing the update rate. Okay. So it's nice to think about what does this do to our system equations, adding this extra term. So this is just the same equations rewritten, right? This is the new update term is the behind thing. And then all I have done is rearrange this equation. Okay, so this previous equation I've added and subtracted a beta term to rearrange it in a form that makes it more intuitive. I mean, we'll see why in a second. But it's the same equation. We should be able to follow, ik plus 1 minus ik is with this 1. There's a minus beta, so that beta terms comes up here. It'll all cancel up to get you the same expression. But once you put it in that form, you see, and again, you take the limits at small sampling time, you get a second order expression. Okay? So this whole thing becomes this second order derivative. This is the first order derivative. And then this is the same as in the diffusion terms. So this is called the telegraphic equation. How information propagates in a telegraph. So it's an old equation. So on the top is the same equation rewritten, right? But what's cool about this, right? If you take beta equal to 1, this gives you the wave equation. Okay? And if you put beta equal to 0, you get the diffusion equation. Okay? So it's because the beta choice will affect your performance of your DSR, but it gives you a nice connection between the wave equation and the diffusion equation. Okay? Because then that, you'll ask naturally, what's a good choice of beta and so on. Right? So one way to think about it, let's assume a local graph. So at that instant, we'll just look at all the neighbors and create a graph, a network graph, and so what that helps you is that this part of the equation you can write in terms of the graph's properties, the network properties, okay, A and B matrices. This is just to analyze the problem. Okay? And you can then take the A matrix and put it in its Jordan form so you can look at the modes. And if you look at the model form of the equation, okay, this looks like a nice second order system. Okay. So I'm rewriting the equation at the top there. And if you do a Laplace transform, you get a nice second order system, and you can choose your beta parameter, which looks like a damping parameter, to be what you want, right? You can choose, for example, critical damping, so you're not having oscillations in the system, and so on. And perhaps the first mode, because that's where most of the information is. Okay? So in this particular example, you can choose it to be the critical damping, so you get a nice expression for that. Once you have that, you can come up with an expression for the settling time for the structure based on the main mode. And this is a settling time without this method, the DSR method, and this is a settling time with the method. And the critical thing here is that there's a square root term here. So for very large systems where the delay is very large, settling time is very large, this has a chance to give you a good performance. And you can see beta becoming small might also have some impact on this, but this is all correlated. Okay, so I have some simulation results for you, just to get to see what happens with these things. Right? Okay. So I did two cases. Yeah. One case is where all the agents are nicely evenly distributed, because that allows me to compute distances and things like that, and how fast things are flowing. And second one is a very randomized system with an agent in the center. And I've played with, oops, did I switch something off?
I don't know if
Maybe
that's
I touched something.
touch.
Oh, there it comes back. Okay, it was just blinking. Update time. All right, so it's 125 agents here. And so the first result here is without the DSR method, okay, without this delayed self-reinforcement. So I've fixed the update time. So we have various parameters you can choose. So we'll start with the update time fixed at around 100 milliseconds. That's what typical animals and birds have. Then increase the alignment. So if you increase the alignment gain, we talked about that. If you increase the alignment gain, your response speed increases. But of course, it could go unstable at some point because it's a stiff system. You can't keep increasing it. Okay. So in this case, here's the alignment gain at about 100. You can see a settling time of around 70 something. And if you make it 101, it goes unstable. So you're at the margin. You can't increase the alignment gain any further, at least without the DSR. If you put a lower alignment gain, it'll go settle even slower. So this tells you that this is the maximum you can do with this method by yanking in the alignment gain. And there's no other parameter left in this process. Okay? So the settling time was 69 seconds. And again, so that tells you that's the limit, right? So now with the DSR, so we'll keep the same alignment gain as the max we had, which is 100. We'll keep the same update time as before, so it's not changing any of those parameters. And then I can search for the optimal beta, the DSR gain, and I found it to be 0.96 numerically. And the settling time goes from 69 seconds to 1.7 seconds. Okay. Now, that's dramatic enough to try this thing out, just to see whether it's going to be useful or not, right? Because it's a simulation granted, but definitely gives you a dramatic improvement. And then the prediction from the optimal beta that I got, which is with a simplified calculation, was about 0.96, is close. So it is what you think should be happening, right? At least in the simulation. All right. So that was kind of cool. Now you have other methods we talked about, right? If you increase the alignment strength to 4039, that's really high. It'll go unstable if you don't change this. It'll become a stiff system, so your sampling time has to go smaller. And that shows up. To maintain stability, you have to have at least a sampling time of 10 power minus 4 in this case. So 0.01, you have to make it about 100 times faster, at least, because of the stiffness of the system. Okay, so that's the thing. So you could increase by using alignment gain. That means but it's still mismatched. It's not like they're synchronizing. They still have trouble. Whereas DSR only gets an update of 0.01. If you take the second order system and still try to do it directly, do a simulation, it still doesn't work. It still requires this really high 10 power minus 4 seconds sampling. So what's different is that the bandwidth needs to be about 100 times faster with these other methods, right? If you try to do it. And even more interestingly, DSR captures the superfluid wave-like propagations. So what this shows here is time and distance the information has traveled. Again, it's time and distance the information has traveled. And so this is a fit. This is the data points from the simulation. So obviously it's scattered because there's reflections, all things happening in this process. And what you can see is in this initial portion, you get this square root of t type effect without the DSR method. Whereas with the DSR, you get this wave-like superfluid motion. And the spread rate, if you look at the slope on an average, matches what you get from the wave-like expression, the analytical expression you'd expect.
But both plots are for the same delay time or the step?
Yes.
0.0.
Yes.
Now, how do you take into account for the larger delay?
For the
what happens in the larger? Are you going to show this or
which larger delay?
Well, if instead of 0.01, for example, you took 0.05.
I tried many things. It's similar. There's not much difference in this approach because if you use a larger delay, then the gain you can do is not much. The alignment gain becomes small, so both of them will suffer equally. But yeah.
But then, do you run into some instability after a certain delay margin?
Oh, you mean in this method? I haven't looked at that. That's a good question. But I have an expression for how much delay you can capture. I'll come back to that. Okay, that's a good point. So I was reading up your paper. Good point. So here's a simulation. And that's kind of cool, right? Again, it's a simulation, but it shows you the ability of this method to propagate the information through. Okay. But the cool thing is, it's actually not such a complicated addition, right? If you are doing those previous control laws for typical networks, that's the typical control scheme. You're not doing that much more work, and it seems to have a benefit, so maybe it's worth a try, right? We are building experimental systems, but till the experimental systems are built, it's hard to say whether you'll get real improvement or not. But the improvement is definitely substantial. You get rapid maneuvers, tighter turns, right? And clearly, even this will break down at really fast maneuvers, but what you're saying is that you get higher performance with this kind of things. So, think in the 5 minutes, perhaps?
Yeah, it's about 1:43.
Okay. So 2 minutes? Okay.
No, you can. We can go up to about 10 minutes.
It's okay. Yeah. So you can also extend this to, we are just looking at neighboring neighbors. You can say the neighboring networks are based on a graph. So you can also do the same thing. But now instead of average of neighbors, you're basically based on a graph, graph network that you specified. The answers are very similar. I won't bore you with that. It's actually very similar results. this was an example where you have a ring, and you see the effect of the ring as you move. And you can see without you get large distortions, or distortions are substantially reduced. But the results are similar, and you expect similarity because the analysis is similar. The extension of time, continuous time systems is very interesting. So here now you have z dot. Okay, so there's a rate of change. So it's continuous time rather than discrete time. And the k and the b terms here are basically the network and the access to the information. So it's analogous to the previous case. Ideally, what you would like is something like this, where each agent has access to the source. Okay, now that's hard to do because you don't have connections. So what this method does is try to do this. If you do I minus beta k here, this z dot will cancel with that z dot. If you bring this to the other side, you can invert the k and you can show that you'll get the ideal equations. Mm-hmm. So that's where it comes down to in the end. Now, of course, you can't do the z dot on the right-hand side because the derivative means you need to know what the other agent is trying to do, and that links to everything. It connects the whole network. You don't have information for that. So that's why you use the delayed version. So you do a zt minus z tau for the derivative. Okay. I mean, other control schemes also do this, right? And at least for analysis purposes. And if you rearrange all these terms, you get this nice classical equation, right? So it starts on the top, which is you have an A matrix and a second matrix, which is delayed. We have the expert on delayed dynamic systems here, delayed differential equations here, right, in our audience. So I did look up several of the papers to figure out what's going on, right? One thing going for us is because of the network structure, we have some nice properties, which makes it proving things a little bit easier. If it's general matrices, it's really hard. There's some nice works on this. But because of the nice structure of our problem, where A and AD has similar structure, and the properties of the graph theory allows us to do some more interesting, more simplified analysis for this specific system. And at least for specific type, I won't go into details, it's in a paper. It's under review, so we'll see. Okay. You can show that this system will be stable if the gain parameter you choose and it's related to all the eigenvalues, if it's on a real axis. You can do the similar version for the complex case too, but that's the essential state. They can come up with an expression for stability, and in this particular case, you can show it for any tau. Okay. Special system, not in general. There was a lot of class of systems which would prove stability under any tau. Those were some of the original papers. For restricted systems, you can show that. And then there's a class of systems that says how much tau you can accept for stability. Okay. And again, you can apply this system. So, since our time is running up, I'll just talk about what I'm trying to do these days. Higher dynamics becomes interesting. If each agent has more interesting dynamics, you'd like to do that. Implementation issues like noise is all interesting questions to see. What are the bounds you get? And then we're trying to do some experiments in the lab. So, to conclude, current swarm models are diffusion-like information spread, proportional to square root of time, and they dampen out over space. But this use of DSR, which is new, I think, for the swarm models, is simple, but it gives you the wave-like information spread, and the information spread can be proportional to time, depends on the choice of the betas. And it definitely increases synchronization, and that allows you to maintain swarm formation. And this does it without requiring additional sensing or increased bandwidth, right, at least for these examples. And at least in that example we saw, there was a substantial reduction in the settling time. So on that note, I'll leave you. Questions?
So before we take any questions, on behalf of the Center, UTC Institute of Advanced Systems Engineering, we have a little gift for you. Thank you for coming to visit us.
Thank you.
Okay. Yeah. So, any questions from the audience, or from the those who are on the telecom?
I'm from the communications background. I actually collaborated with Sumi Roy from University of Washington.
Oh, okay. Yes.
So we collaborate on project.
I see.
So when I see the information, I always talk about data rate, reliability, etc. So like in your simulation or in your experiment, what would be the amount of data needed?
Yeah.
Like, because what is the bandwidth you're talking about, right?
Yeah. So there are various ways to look at that. right? So you can talk in terms of how many bits you can send per second, and then you can try to see what kind of control stiffness you can get and things. So there's a class of people who do that kind of work, right? So in our case, I just made it simpler by saying I'll limit the time you have. I mean, you can't go less than that sampling time. So the assumption is that whatever communication limits you have are accounted for that limit in the sampling time.
The sampling time is about delay, and I noticed you have chosen a very nice delay, which is 0.01, which is 10 milliseconds, right? 10 milliseconds happen to be the frame update rate of the cellular phones.
Oh, is that right? Okay.
Yeah, that's 10 millisecond simple time slot.
Yeah.
Okay.
Yeah, I was thinking of reaction times, so humans
that
and
is
things like
one frame delay if
okay.
you think go through the 5G network or 4G network, right? So but then is within that 0.1 of 10 millisecond delay, how much information do you need? Like what data rate, like the megabits per second, etc. So we have a delay issue, and also we have the bandwidth issue, how much information. So I just say curious for those type of applications, right? Really, how much data need to be go through the system and subject to delay. The frame delay is 10 milliseconds.
Right. Now, those are really good questions that I hope to explore someday. Clearly, the amount of communication you need, and when you access the bandwidth, right, all these things will come into how quickly you can update yourself. Okay? And so all of that stuff. So this model that we have for swarms is the simplest model that people have, right? And it captures most of it. Why? Because it captures all those inherent birds. They're also communicating. They're also looking at things. They're sensing, right? They're computing in their brain and then reacting. So the delta T that you choose can be specific to your problem, based on your data rate requirements, based on your actuation requirements, and so on. So you can say, I cannot go below this. Right? So that's one way to look at the simplification. Of course, you can look at from the other side and say, how close can you get given your communication requirements and so on, right? So this way of thinking is to try to simplify that from the controls point of view, because there's other issues inside, right? And so this delta can be specified by you based on the problem. And so there's definitely a lot of need for research into trying to figure out what should you need inside that, right? I agree.
Yeah.
I'm with you.
That's great. And once you couple with communication problem, those packages also arrive there, like not error-free.
Absolutely.
Then you would have some wrong information.
Absolutely.
And how do you...
Yes.
So that's complicated.
I'm fully with you. I mean, in simple models, you can see there are synchronized updates too. So you expect things to go wrong because of that. You expect things to be... So that's why when you do something like this, you take the simplified version first because you want to understand the stuff, right? And then suddenly there's a lot of interesting questions that in this future work, I'm certainly interested in finding what happens when you have offsets in the timing, right? So but when you see a big difference in the performance, then you think maybe there's potential to do something more. And I hope to think about these questions. Yes.
Yes, the information here are like the turning races. Yeah. So perhaps emotion control applications. The information is not huge compared to...
but it could be velocity. So in this, for example, in the bots example, in driving of cars, you're just looking at the forward velocity, and you're just using that to synchronize yourself. So it may not be as bad, but still, you have to think through it carefully. And there may be some relationship between that and how much performance you can get, for sure.
Any other questions?
Yeah, very interesting talk. Thank you. Gamma, that parameter, is there any intuition with that? I just noticed it was 1 over delta for your example, and then 1 plus that was unstable. Is there some kind of reason for that, or what's?
Yeah, I mean, if you have a discrete time system, right? So if you think about the way, if you work it out, the equation will turn like 1 minus your previous A. That's basically stability theory. Okay, so it's 1 because it's xi. Maybe if I can find the equation, let me see if I can do that. Yeah. So typical expressions that you have is the next state is the old state, so like I 1 here, and then minus something times the how your structures relate to each other. That's your A matrix. So the stability depends on I minus gamma times A, right? So if you think about a scalar case, the eigenvalue of this is, let's say, little k. So it'll be stable if y minus gamma k is between plus minus 1. So if you choose a very large value, you can go unstable. right? It goes outside the unit circle. And so that's the fundamental limit. So as you yank up your gamma, right? Effectively you made a stiffer system, so the eigenvalues are big. So the only way you can make this system stable is if your delta t is small.
Okay.
So it's a nice relation between the structure of the problem, which is eigenvalues, delta t, and gamma. But that's a well understood problem,
Thank you.
So, if I may add another twist to this the time delay reasons. See, what has been an intriguing topic on the injection of time delay is always the possibility of violation of delay margin and inviting instability in a certain regime.
Yes.
And then forcing yourself to increase the delay as a counterintuitive proposition and regaining the stability.
Yes.
And we have run into these sort of circumstances some 3-4 years ago, published on this. And of course, this goes without saying that in real-time applications, in real-time controlled implementations, there will be a lot of parameters that will play into this. But if there can be a possible mechanism, decentralized control mechanism that can allow larger delays recovering the stability.
Yeah, I had a wonderful talk.
Wonderful thing.
Yeah, I had a wonderful talk with you, so that was really inspiring. So let me mull over that. That's a good problem. So so when I first started out, I didn't know that all this delay history a little bit. So I started reading up on it. So sabbatical gives you some time, right? So it was wonderful to follow the history of the different people trying different methods and how to do delays. And I read your 2002 paper. It was really good.
It is incredibly titillating.
Yes,
if I can say that. That the machine tool specialists know this by heart, and since 1960s, 70s, they have been fiddling with time delay.
I see.
The spindle speed is equivalent of the inverse of time delay, the frequency of the machine cutting.
I see.
And they have found the time delay stabilizing elements when the delay is increased, when it happens. It's experimental.
Right.
And very much, by trial and error, sort of. But there is a mathematical reason behind it.
Right. Yeah. No, that, and also, Gallups' paper was very interesting for me too when I read that. That gave me some idea. So clearly, there's Lambert functions are there. There is this method of the J omega crossing, and then there is this theory that for any delay, right? There's a class of problems that you can show stability for any delay. So there's these three things that were quite inspiring as I was going through this. But I think this is just a start. I just began, worked on this for about 6 months of my time when I could. But I think we're just starting out. Certainly communication issues, asynchronization problems, noise issues, high order dynamic, all this comes into picture. And there's some really good papers in recent works that talks about bandwidth, how many bits you can send versus what you can do with controls, right? And so there are some really nice analogs that can be brought in. So I think I'm just starting out on this journey. So okay.
You know where BigSec is these days?
I don't know.
I lost track of his most recent development. These are.
I haven't seen his papers recently. I've seen other groups publishing, but I haven't seen his papers recently.
In Science and Nature, they published some 10 years ago.
Right. Yeah.
Excellent.
Thank you.
Okay. I have a little question. So it seems like the way the architecture changes is finding a balance between diffusion and wave equations. Both areas have a lot of implementations, especially in mechanical engineering fields. Is this somehow maybe suggesting some sort of a fusion between these two, actually introduce interesting properties people can look into?
Could be. Telegraphic equations have also been studied because of that same questions, right? It captures some of the actual physics.
Mechanical engineering people seems to have not dived into
telegraphic equations.
Right?
Yeah, it was new to me too. Right? Yeah, but fluid mechanics people, I was studying with my colleague who's a retired faculty member. He's in nuclear engineering, And he said, well, yeah, that's a telegraphic question, so, yes, that's right. But, that's why I remember when I started out in research, somebody told me that's why it's called research, searching again, right? So you find new things every time you look. And that's what keeps us interested in the whole thing, right? I mean, finding new things and looking at it and so, ooh, this is something cool.
Okay. Any other questions? If not, let's thank the speaker again.